All right, so we're talking about populations today. And so what is a population? We've talked before about what a species is. To be a member of a species, you must be able to create grandchildren together. So if you're a human, you should be able to make grandchildren with other humans. That's pretty much the rule. It's not enough to just have children, right? Because there are some organisms out there that can't do that. There are some animals, like for example, if we mixed a lion and a tiger, we do not get a lion or a tiger, we get a liger. A hybrid is an organism that cannot have babies. It is infertile. The reason for that is genetic, and we'll actually talk about that during our genetics chapter. But hybrid animals like a liger or a zebra and a horse is called a zorse. They can't actually reproduce, and so they are not members of the same species. But when you have a species, you can talk about the entire species. Like, for example, the human race. We could talk about humans. That would be a species. But we could also talk about populations, which is when we include an area. So, for example, there is the U.S. population. There is the Mexico population. There is the population of Spain. There is the population of China. There's the population of the Eastern Shore. So we have to talk about an area when we talk about populations. It's not just a species, but a certain species in a certain area. Then there's communities, which is multiple species. So not just the humans in the area, but the dogs, the cats, the squirrels, the raccoons, all together. That is a community. Communities, along with the abiotic part of the environment, make an ecosystem, and then an ecosystem classified together with other similar ecosystems is a biome. And so we've already talked about most of this today. We're talking about populations. And so what is a population? Again, a population is a group of organisms of the same species that live in the same place. So we are concerned with place and number. And so, for example, when talking about a population of deer, we wouldn't just say, oh, there are 3 deer. We would say there are 3 deer per unit area. And so when we talk about unit area, we could talk about meters. We could talk about miles. We could talk about per acre. We could talk about per kilometer. There are lots of different ways. We could even say per inch. Like when we talk about bacteria, we tend to measure them per inch or per millimeter. So we could use a lot of different units for area. And so, for example, if I were to tell you that there are 3 deer per mile versus 3 deer per inch, which one is a greater density? Well, obviously it's this one. That would be a lot of deer. That would be like 3 deer standing in one place. Whereas these 3 deer have a whole mile and they can space out more. So this might be 3 deer per mile. These deer here are sharing 1 inch, so they are right on top of each other. Here's why we use density when we talk about a population. So sometimes there are just too many organisms to possibly count. So for example, if we were to measure how many blades of grass there are growing at a school, like Arcadia, it would take a long time to count them. And so instead of counting them by hand, all of this grass here, it would be better to get a measure of density first. And so what we do is we set up little grids. Inside of those grids, we count how many of those organisms there are. We add them together. And we divide by the total. So let's see, that's 7 point something. So I'm just going to say 7. And so for here, the average would, well, it's closer to 8. For here, I would say the average number of blades of grass per unit area is 8. And I'm going to say that these pink boxes are meters squared. So 8 blades of grass, well, probably per foot. 8 blades of grass per square foot. And we're calling it a square foot because these are squares. And so then what we would do is figure out how many square feet there are here in all of this land, and we would simply multiply. So if there's 8 per square foot, and let's say that the amount of land here is, I don't know, 300 square feet, then how many blades of grass are there? Well, that's simple. You simply multiply by 8 to get your total, which would be a lot. Let's see, 8 times 3 is 21. So that is a whole lot of grass. So that'd be like 2,100 blades of grass at this school. If you understand. So let's say that we have 3 densities for these deer. Let's say that there is 100 deer per 100 miles. Let's say that there are 10 deer per mile. Let's say that there are 10 deer per meter. Which of these would be the greatest density? Okay, so to figure this out, we simply divide, right? For the first one, 100 divided by 100 is just 1. So that would be only 1 deer per mile. Whereas over here, 10 is 10 deer per mile. Obviously 10 is greater than 1, and so this is the greater density. However, the third option is the greatest density because that is not 10 deer per mile, that is 10 deer per meter. And so 10 deer per meter means that there's a whole lot more deer closely together. So this might be 10 deer per meter. So 10 deer per meter would be the greatest density. Let's talk about how populations can change. When a population is not changing, it is at equilibrium. What can disturb equilibrium? Population size is affected by birth rates, death rates, and migration into or out of a population. There are 2 types of migration. There is immigration with an I and immigration with an E. They sound the same, but they are different. I like to think of this one as moving into an area. That's why it starts with an I. And this one is moving out, or to exit. Those are the two types of immigration. So this would be to exit, and this would be to enter. And so we call this one immigration with an E. And we call this immigration with an I. Both are types of migration. So these are two factors. So obviously this would increase a population and this would decrease it. And then birth rates would increase it, and then death rates would obviously decrease it. And so to calculate this, it's very simple. It is birth rate minus the death rate plus migration, which is immigration with an I minus immigration with an E. And that equals the change, or the rate of change in population. Okay, so populations will initially grow when they first come into an area. And so this growth is very fast. We call it exponential. And it can only occur when conditions are ideal. The key word there is ideal. Remember that word. Ideal conditions means that there is plenty of food, there is plenty of space, and nothing limiting you. And so we can have no limiting factors. Limiting factors keep populations down. They set a bar. And we could represent that with a dotted line usually. Limiting factors set what's called a carrying capacity. Exponential growth will stop if there is a carrying capacity. But when there are no limiting factors, there is no carrying capacity. And so the population will just continue to grow and grow and grow. The human population is like this. We are growing and growing and growing, and nothing seems to be really slowing us down, other than education. And so, it is inevitable that all living things eventually stop growing exponentially and they start growing logistically. Once that carrying capacity is established, the population will start to slow down and they will level off. And so there are three parts to logistic growth. There is the first part, which looks just like this, and that is the exponential part. All populations start like this. And then there's the second part where they begin to slow, and there's the third part where they level off. Inevitably, all populations eventually become logistic. Even humans will eventually level off. Something will keep us from growing. Something will be our carrying capacity. It almost was COVID. It very well may be some other disease that comes along. So the things that make this carrying capacity are called limiting factors. And I want to be clear, a carrying capacity is never in one place. That is why it is a dotted line and not a solid line. It can go down if resources are limited, or it can go up if resources increase. It can go down if there is disease, or it can go up if you create medicine. It can go down if you are having war, and it can go up if there is peace. There are many things that determine where this carrying capacity can be. And so often when we look at populations over time, you'll see that they fluctuate like this. That is because during one part of the year, the carrying capacity might be here, but during the next, it is way down here. The carrying capacity quite frequently will move. And so what sets that carrying capacity is the limiting factors. And there are two types. There is density dependent, which is on this slide. And then there's the other one, which is called density independent. And so we'll start by talking about the density dependent. These are things that depend on density. And so the greater the density of a species, the greater these factors affect the carrying capacity. And so these factors include things like competition. The more organisms in an area, the more they must compete with each other. The more prey, the more predators. The more people, the more COVID. Right? So these are things that increase with more people. Competition for resources can occur within a population or between two different species. When talking about density dependent factors, we just mentioned competition, but another thing that can limit the size of a population is disease. And this is because when there are more individuals, parasites, bacteria, and viruses can move between those individuals faster. So if this guy right here is sick and he is in a densely populated area, he can quickly spread his sickness. And then those goats can then infect their neighbors. This will rapidly spread a disease. Whereas if there were only a few of these sheep, they would not be as affected. And so, as the population, let me see where I can draw this. As the population of deer, these are sheep. As these sheep grow, so does bacteria. Until eventually, it starts affecting the population size. And so in this instance, the carrying capacity is set by the parasite. So this is still a density dependent factor, because as the density of the sheep go up, so does the parasite. Density dependent factors are influenced by density. Take, for example, a zombie apocalypse. Obviously, there is more density in the city and not a lot of density outside of the city. And so, where would you rather be during a zombie apocalypse? Go ahead and answer. Density dependent factors can include predation. This is because as the density of the prey increases, so does the density of the predator. So as the density of the prey increases, so does the density of the predator. That makes it a density-dependent factor. When we talk about these, we can actually predict how populations may fluctuate. Fluctuate means to go up and down. So for example, if we look at the rabbit does very well. It grows exponentially. And then, as it grows, so will the number of wolves, or in this case, coyotes. Once those coyotes reach a certain density, they will start to decrease the density of the rabbit. Once the density of the rabbit is very low, the coyotes have nothing to eat. And so their density will also decrease. Once the coyotes are low, this will allow the rabbits to then grow again. But because they have grown, so will the density of the coyotes, making their numbers go down again. In such a way, both predator and prey will fluctuate. Such information can help us when we are trying to do things like determine when a hunting season should be opened.